time, exactly the same time, that may cause the problem. Okay? How many keys to access the root? Only one key, which means mutual exclusion, which means if one of the process is executing or entering such a critical section, the other processes should wait until this one is completed. So that is called the mutual exclusion. Okay, it's easy to understand. The next one is the progress. It's not easy first time to understand the definition of the progress. Progress means if, in this case, two processes, okay? In this case, two processes, if one process is enter the critical section, there might be the other process who is in the entry section, okay? Entry section. Then, once this process is completed in the critical section, then which means going to exit section. Then at that time, the other processes who are in the entry section need to decide who is the next one. As I explained, for example, we have students who want to access the bathroom. Okay, so at that time you need the key. So if I assign the key, I try to give the key for those who are very nice student only or handsome student. So it's not fair. So forget about the operating system control that. Or if the student who use that bathroom decide the next one, probably you can give the key to your best friend. So those who are waiting for the bathroom, okay, need to decide how. Sometimes you make the line, okay, first in, first out. Those who are not in the line, for example, who are in the outside the building, they don't have to, okay? So only processes in the entry section need to decide who enter the critical section, okay? So that is the second requirement, progress. What about this algorithm? Does it satisfy with the mutual exclusion? Or not? Yes? The first requirement. Yes, how many processes can enter critical section? One, only one. Okay? What about the second, progress?
They enter the critical.
Yes? No? Who decide the next one? This process decide. It's turn. Key is the I, J. Key is the I. Right? Even though this situation, only two processes are involved. It's like that. So when you use after you use the bathroom, you give the key to the J or I or you assign. Okay? It's not fair. Why? Because some of the students wait forever if the student is isolated. Right? So this algorithm is simple to understand, but it doesn't satisfy with the second requirement, progress, because of this exit algorithm. This can be used in case only two processes. Right? This is, even though this algorithm does not satisfy with the progress, but it can be used for only two processes. Why? Because you can assign only one, the other. And third one is bounded waiting, which means there might be many processes in the entry section who are the number of students who are waiting for the bathroom. So there are number of, let's say 10 or 20. They should not wait forever. That makes sense. In other words, bounded waiting. There might be But the problem is bounded waiting does not mean fast. Okay? There is the maximum wait. It can be 1 year, it can be 10 years, it can be 100 years. But it's not forever. So bounded waiting does not mean it's a fast. Okay? It's a guaranteed. How long? It can be 1,000 years. It's a guaranteed. It's a bounded waiting. Anyway, it's an upper bound. But in terms of algorithm, eventually, we don't care how many. It depends on the algorithm. But eventually, the processes in the entry section will get the key. Will enter critical section. Those who are in the waiting line should get the next step. Sometimes later we'll get the key. That is the bounded waiting. Okay? At this time it doesn't consider how fast is that, but it's the bounded waiting in terms of algorithm. So that's very important when you if you are the PhD student or some thesis option master student, so you propose algorithm idea. So you need to prove it. So my algorithm is the upper bound. Okay? Or lower bound. You need to prove such a thing. How? For example, limit. This is go to 0, something like that. It's the lower bound. Okay? Value is going to 0, but it's not less than 0. Such a way you need to prove it. So this critical section problem algorithm should not forever. It's a bounded waiting. 3 requirement. Mutual exclusion. So no other process will enter, only one process will enter the critical section. And second is progress. Progress means the processes in the entry section will decide the next one. It's called the board. Okay? The remainder section, they do not involve such a body. Also, this section cannot be postponed. If you allow postpone or block this part, you cannot select the next one. The last one is a bounded waiting. Okay.
Now it is number 2 and number 3 is depends on the algorithm.
Yes. Also, number 1 is the requirement of the algorithm. Some of the algorithm may allow the multiple process. They may cause the race condition also. So, most important thing is number 1, the mutual exclusion. Then the number 2 and number 3 are for fairness. Okay. So some of the algorithm cannot guarantee 2 and 3, and in certain case, like this kind of example, because you have only 2 processes. So even though this is in terms of the algorithm, it's not satisfied with the progress, but anyway, the other process is only 1, so they will get eventually they get the key. So to implement, so we don't discuss yet what kind of, this is one of the examples we will see. The next class, one more, the details of it. But to implement such a critical section problem algorithm, there are different ways. So we can classify into 3. One is the software solution. What about this one? Is it the software solution?
Yes.
Yes. I do not use any other structure, any other hardware, any other operating system for or whatever. It's nothing but my code. So it's the software solution. But it may cause the busy waiting. What does that mean, busy waiting? During the waiting, because I really wanna go to the bathroom. So you keep asking, knock knock door, knock knock door, knock knock door. So when you are done, when you are done, when you are done, when is my turn? Keep asking. That's the busy way.
Timer.
Like this one. It's an infinite loop until it's changing, right? If you see the percent of the CPU, it will be very high. It's an infinite loop until you change the value. Okay, that is called the busy waiting. Because you are using software anyway. In your code, how can you block the push? You need to use such a thing by checking the turn value, key value. So you keep asking, is it done? Is it done? Is it done? Okay? Because nobody informed to this one. Actually, you need to check. So that is the busy waiting. There might be busy waiting problem in software solution, but it's easy to implement it. Hardware solution, we have the hardware structure, okay, such as a semaphore. We will see what is a semaphore, and there are a lot can be implemented in the hardware structure in your motherboard or CPU or something like that. We can use such as some special machine instruction, okay, for that. Operating system solution is in your operating system you design some data structure. Okay, it's not hardware, but it's the operating system level, which means it can be controlled by operating system. Okay, for example, the professor provide certain the box or the sign, LED sign. It's the bathroom is using currently they're used by the student, and once it is done, then give the signal. So I'm not going to involve to decide who will purchase the key, but I will give the information and I will give the such a routine board. Okay, so you can use such an operating system structure to implement such a algorithm. There are different types of algorithm. Okay. Okay, so I will stop today's lecture here. So we will see the sum of the software solution for critical section problem and the hardware solution as well as the operating system solution in the next class. It's a very good example of the midterm exam. Right? Okay.
Do we have lecture next Tuesday?
Oh yes. So I got confused. So I thought it's already done. The faculty